Hello everyone, this is Dr. Sharif El-Gamal again with you, and today in this video I will give you a second part number 2 about plastic analysis of structures. In this video I'm going to talk about elastic and plastic moment calculations, then we will see how to calculate the shape factor, load factors. Also we'll know about collapse mechanisms of the structures and how to calculate the collapse loads. First of all, how to calculate elastic and plastic moments of a cross section, because we need these two values to get the shape factor of that section. For the elastic moment of resistance, we call it M elastic, and sometimes you call it M yield. We have two different methods that we can use to get this M elastic, or the elastic moment of resistance. The first method depends on the famous law that the stress equals M over I times Y. The stress, so we can say the yield stress equals M elastic divided by the I times Y. Where is the I is the moment of inertia of the cross section, and Y is the distance from the neutral axis to the outer surface of the section. So let's see here if we have a beam and we have a rectangular section. So the section will be with a width of B, and the h is the height is h. Because of symmetric, the neutral axis will be exactly at the middle, at h over 2 at the top, h over 2 at the bottom, and this will be the stress distribution. And as you can see here, it is linear because we are still in the elastic range or the elastic stage. So if we assume that we reached the F yield, okay, at the top, F yield at the bottom because of the symmetric of the cross section here, so we can calculate the M elastic or the M yield. Okay, how to do that? We are going to use this law here. So if the F yield equals M elastic divided by I times Y, as we can see here, so we can rearrange this equation and we can calculate the M elastic. So the M elastic equals F yield times I divided by Y. So it will be F yield times I divided by Y. This value here, this term I divided by Y, we called it S, as we have seen in our previous video, part number 1, and it is called elastic modulus. So the elastic modulus of a cross section equals the moment of inertia of the cross section divided by the Y. Okay, so if we want to get this as values for this cross section here, so let's calculate the I and then we calculate the Y. I, as you know, for a rectangular cross section equals B times h cube over 12, BH cube over 12. Y is the distance from the neutral axis to the outer surface here, so it is equals h over 2. So by substituting these two values, I here in this equation, Y also in this equation, we can get the S. So the S equals I divided by Y, BH cube over 12 divided by h over 2. So remove h here from h cube. So at the end, you will have the S, or the elastic modulus, equals BH square over 6 for a rectangular cross section. Substitute this value S here into this equation. So at the end, the M elastic equals F yield times S equals F yield times BH square over 6, where this BH square over 6, as I just explained, it's called the elastic modulus, and we give it the term S capital. This is the first method using the stress equals M over I times Y. Can we solve it using another method? Yes, we can get the elastic modulus using another method, also using the stress distribution here, but we'll get the resisting moment from this equilibrium. So for this stress distribution, we have F yield at the top, F yield at the bottom. This distance is h over 2. So we have a compression force at the top, we have tension force at the bottom, Fc or Fpt. Both of them are equal because of the equilibrium. The summation of forces in the x direction or the horizontal direction should be equal, so Fc equals Fpt. If we want to get the moment of resistance, we can take a moment at the position of Fpt. So the moment in this case equals Fc times L elastic, this lever arm here, or it equals Fpt times L elastic. Okay, so we need to find L elastic and we need to find this force. Okay, For this force here, FC equals the area of this triangle here times the B, the width of the beam, or the average value here times the area of the beam above the neutral axis. So the area of a triangle equals half times F yield times H over 2. So FC equals FT equals half, because this is a triangle, times F yield, this distance here, times the height of the triangle, H over 2. Okay, we get this area, multiply by the width of the beam, so we can get the total force, which is called FC or FT. They are the same here, and always they are the same because of equilibrium. So at the end, recalculate these values here, so it will be F yield times BH over 4. Okay, we found the first part, FC and FT. How about this lever arm? As you know, for a triangle, this resultant load will be at a distance of 1/3 from this base here of the triangle. So if this is 1/3 of the height of H over 2, so the remaining part will be 2/3 times H over 2. So if you have this distance here, 2/3 H over 2, and from the bottom it will be exactly the same. So 2/3 times H over 2 times 2, because of the two values. So it will be at the end 2/3 times H. Okay, if we have the L elastic, we have the force. So to get the bending moment or the resisting moment, in this case it's the elastic moment, equals FC times LE. So multiply this factor here, their value here, F yield times BH over 4, times the height here, or the lever arm L elastic, equals 2/3 times H. At the end, it will give us similar value as the method number A. And again, this is the elastic modulus, and it equals to BH square over 6. But this is only, keep in mind, this is only for a rectangular section. For different types of sections, you will have different values, of course, of the elastic modulus. So these are the two methods that we can use to find the elastic modulus, elastic moment of resistance. Okay. How about the plastic moment of resistance? The plastic moment of resistance, or we call it M plastic, we have only one option, which is to use the method number B, because method number A, it requires linear. And in the case of plastic analysis here, we don't have any linear anymore. It is full plastic stage here for the whole cross section. So the stress distribution, it is FP yield and a constant value. And then at the bottom again, it is FP yield, but in tension and also constant value until reaching the neutral axis. So we have to get it in this time using the force times distance. So FPC again equals FPT and equals to this area times B, okay, or equals FP yield times B times H over 2. So this is FPC equals FPT equals FP yield times this area here, which is B times H over 2. FP yield times B times H over 2. How about this L plastic in this case, the lever arm in this case, we call it L plastic because we are dealing with a plastic stage. So it is very clear here for a rectangle, this will be exactly at the middle. So here it will be half of the H over 2, it means H over 4. And here H over 4. So H over 4 plus H over 4, it equals H over 2. Then to find the M plastic equals FPC times LB or FPT times LP. So it equals FP yield times BH over 2. This is the first term, times the height L plastic equals H over 2 by getting the value here. It will be FP yield times BH square over 4. And this term here, we call it the plastic modulus, or we give it the letter Z. So the elastic modulus is capital S, the plastic modulus of the cross section is called Z. You should have the plastic modulus, Z should be greater than the elastic modulus, because a cross section cannot reach the full plastic stage until it will go through the elastic stage at earlier stage. Okay, so it should go to elastic first, or the yield first, and then this yield will continue until the whole cross section will be fully plastic. And in this case, we can reach the plastic modulus or the Z. So if you are calculating the S and a Z in a problem, and you got the Z less than S for the cross section, you know that there is a mistake, because you should know that the plastic modulus, the Z, should be greater than the elastic modulus of the section, which is called S. Once we find Z and we find S, we can now go to a shape factor and we calculate the shape factor, and we give it a letter gamma here. The shape factor of a cross section equals M plastic divided by the M elastic, the plastic moment divided by the elastic moment. Okay, and the plastic moment equals F yield times Z. Elastic moment equals F yield times S. So we can, instead of using M plastic divided by the M elastic, it will be directly Z over S. Plastic modulus divided by the elastic modulus. This is the shape factor. For different shapes, for different cross section, you have different shape factors. Like in this case, if we are dealing about rectangular section, the Z was BH square over 4 as we calculated, and the S was BH square over 6. So if you calculate the values here, it will be 6 over 4 or 1.5. So the shape factor of a rectangular section will be always 1.5. Okay, so if you know, if you have a cross section which is a rectangular, you know directly that the shape factor will be 1.5. But for other sections, you will have different values of shape factor. Like I-beam here, it is something close to 1.15, could be less, could be more, but something around this value. As I told you, for rectangular section, it is 1.5, and for a circle, it is 1.7. For like something like a diamond here, it will be 2. So you should know that for different cross sections, you expect to have different shape factors. The one that you need to know is when you have a rectangular cross section, you know directly that the shape factor is 1.5. Okay. What is the significance of shape factors? It can help us for few things. First, it gives an indication of reserve capacity of a section from yielding at extreme fibers to full plastic. Okay, if you have higher value of a shape factor, so it means you have more reserve capacity. It will reach the yield first and will take more time to reach the fully plastic stage. If the ME is known, we can calculate the M plastic. If the M elastic is known and I know the shape factor, I can directly get the M plastic, because the shape factor equals M plastic divided by M elastic. So if I know one of them, I can get the second one if I have the shape factor of the cross section. Also, a section with higher shape factor gives a longer warning before collapse, because it will take time to reach the fully plastic stage, and then it will go to unstable stage based on the number of plastic hinges that will form. Again, also, higher shape factor is more ductile. If a section has higher shape factor, it is more ductile and gives greater deflection at collapse. Again, it is like giving more warning. And finally, greater is the shape factor, greater is the collapse load, or we call it lambda collapse or lambda C. What is this collapse load? We will see now. The collapse load here of a structure is the minimum load that results in a collapse of the structure. So if you apply a load on the structure, okay, the minimum load that will result in a collapse of the structure, this we call it a collapse load. So of course, when you design a structure, you don't want to reach this collapse load, otherwise you will have a collapse of your structure. Okay, so this is the collapse load, the minimum load that will result in collapse or a collapse of the structure. Collapse load can be found for a structure by investigating various possible collapse mechanisms of the structure. So for a structure, sometimes you will have only one collapse mechanism, especially if you are dealing with determined structure. Okay, if you have indeterminate structures, especially if you have like continuous beam or frames, you may have more than one collapse mechanism. So to determine this collapse load, you have first to investigate different collapse mechanisms, and from each collapse mechanism, we'll calculate the load that will result in this collapse mechanism. Okay, then from different collapse mechanisms, the minimum collapse load will be the governing collapse load, and that mechanism will be the governing collapse mechanism. If you have only one collapse mechanism, so you will have only one collapse load. If you have more than one collapse mechanism, you will have more than one collapse load, but the minimum load will be the governing collapse load. How to calculate the collapse load? Okay, collapse load of the structure, to calculate it, we have to follow the following steps. First, we have to assume possible collapse mechanisms and draw them and showing the displacement and thetas at both ends of the beam. Let's say, for example, here, if we have a beam, which is a simply supported beam under concentrated load, which is called WC, at a distance here 0.75 L and 0.25 L. For a simply supported beam, it is a determined structure, and as you know, in our video number 1, for determined structures, you need only one plastic hinge to reach the collapse mechanism. So, and this plastic hinge will form at the position of maximum moment, in this case, maximum positive moment, so it will form under the load exactly. So, if you know this, you have to draw the plastic hinge and draw the collapse mechanism like this. Under the load, you have a displacement called delta, and you have a theta A and you have a theta B. If you extend this line here, the angle here will be equals to theta A plus theta B. Okay. So once we did that, we need now to find delta in relation to theta A. We need to get theta B in relation to theta A. So we need to get only one angle, and everything will be related to that angle. Okay. So to get the delta here, delta, or this theta A is very small. Okay. So if the angle is very small, we can assume that the tan angle equals the angle itself. So tan theta A equals theta A, and the tan the angle equals delta divided by 0.75 L. Then from here, rearrange and get the delta. So the delta equals theta A times 0.75 L. So we got the delta using the theta. So it is the delta equals distance times theta. Okay, 0.75 L times theta A. Now we need to get the theta B in relation to theta A also. This can be done easily from the triangles. We can say that theta B equals theta B divided by theta A equals this length here divided by this length. So theta B divided by theta A equals the far length 0.75 L divided by the near length here 0.25 L. So 0.75 divided by 0.25 equals 3 theta A. So theta B equals 3 theta A. And it is important to draw this like using a reasonable scale or like a logic drawing to know that, because if you make a good drawing, you will know that theta B is greater than theta A, so you are not going to make mistakes. Once we calculated delta and using the theta A, we calculated theta B using the theta A. So now to find the collapse load, we have to make equilibrium between the external work or work done by the load and the internal work in the structure, which is the work done in the plastic hinge. We have work due to the load. As you know, the work equals load times displacement, or equals moment times rotation. So the external load equals W external, the external load here times delta, it will give us external work. And the M plastic at the plastic hinge, because at the plastic hinge we have a value of moment called M plastic. So it will be M plastic times rotations at the plastic hinge, not any other rotation, only rotations at the plastic hinge. Let's do this. So we can say external load or external work equals internal work. Work done by the loads equals work in the plastic hinges. So the work done by the load equal load times linear displacement under the load, which is delta, or in this case, it is 0.75 L times theta A. How about the work in the plastic hinge equals the plastic moment, or the moment in the plastic hinge, which is called M plastic moment, times the theta here, the angle. So the angle here, which is theta A plus theta B. Let's put these as values. So external work equals WC times delta, which is 0.75 L theta A. This is first term here. How about the second part? Internal work equals M plastic times theta A plus theta B. And as you know, theta B, we found that it is equal to 3 theta A. So theta A plus 3 theta A, it will equals 4 theta A. Now rearrange, or if you want to get the WC, the collapse load equals 0.4. We remove theta A and theta A here, so the remaining part it will be 4m plastic divided by 0.75 times L. So 4 divided by 0.75 equals 5.33 m plastic divided by the L, and this will be in kilonewton or in the force unit that you are using. Usually it is kilonewton. And here we have only one collapse mechanism because we have only one collapse load and because we have only one collapse mechanism. So if you have only one collapse mechanism, like in this case, indeterminate structures, so you will have only one collapse load and will govern our design. Finally, here, I'm going to talk about load factor. What is the load factor? Lambda C. The load factor is defined as the ratio of the collapse load to the elastic load. Okay, so it is the ratios between load. Load factor in this case, lambda C or load factors equal W collapse divided by W elastic. W collapse, similar to what we just used. W elastic, we calculated from the elastic stage using regular equation for the moments, or if you have, it could be a fixed end moment in case if you have one span with fixed end moments, you can do it easily. This is similar using regular equations, and this collapse as we did in the previous slide. So the ratio between W collapse divided by W elastic, we call it load factor. This is the end of the second video. In the coming video, we'll go through some solved examples about different collapse mechanisms of beams, different collapse mechanisms of frames. Will be in video number 4. Thank you for watching and goodbye.